Today I would like to discuss Atwood machine problems. Okay, here's a typical Atwood machine. You have a pulley and two objects, a 5 kilogram object and a 15 kilogram object, are attached by a rope over a frictionless pulley. Now obviously it wouldn't stay like this in equilibrium. It would actually move clockwise. And not only would it move, but it would accelerate because this weight is greater than this weight. So I'm going to lead you through a series of questions so you can best understand this type of problem. So what's being accelerated? Well, both the 5 kilogram object and the 15 kilogram object. And in what direction? Well, they're both going clockwise. What's making it fall? Well, what's making it fall or go clockwise is the weight of this guy. And then you say to yourself, well, what's holding it back? Well, what's holding it back is the weight of this guy. So what's the acceleration? Well, we'll apply Newton's second law, F is equal to ma. And we take the sum of the forces. Here's the force making it go clockwise. Here's the force making it or holding it back. What's being accelerated? Both masses times acceleration. So in summary, this is making it accelerate. This is a force pulling it down. This is the force pulling it back or holding it back. The combination of those two forces equal mass times acceleration. What's being accelerated? Both masses. So let's try a different example. Now we have the same type of frictionless pulley, but this time we have the 5 kilogram object sitting on a table. So what's being accelerated? Well, if they're attached again, both of them are being accelerated. In what direction? Once again, clockwise. What's making it fall? Well, the weight of this guy. What's holding it back? Well, you may think that it's the weight of this guy, but it's not. There's nothing holding it back since it's frictionless, and the weight of this guy acts vertically while this is being pulled horizontally, and y has nothing to do with x. So what is the acceleration? Once again, we'll apply Newton's second law. So we take all the forces. In this case, there's only one force, the weight of this guy, is equal to mass of both objects because they're both being accelerated, times acceleration. And one last example. All right. Now we do have friction, so it's the same setup as before, but we have friction, and I have a coefficient of friction of 0.2. So what's being accelerated? Both of them again. In what direction? Once again, clockwise. What's making it fall? The weight of the 15. What's holding it back? Well, now the force of friction between this object and the table. So what is the acceleration? So we're going to apply Newton's second law. We have to sum up all the forces. The positive force would be the weight of this guy, right? What's holding it back? The force of friction, pulling it back the opposite way that it wants to go. And what's being accelerated? Both masses. And since we know that this is on a horizontal surface, the force normal is equal to weight. And therefore we can put the numbers in and solve for A. And that's pretty much what Atwood machines are.